We are live. So good morning, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world, and we are particularly excited. Usually November is our space month, but this year we've changed it up. It's all October long in honor of Space Week. So we've got over 60 sessions this month dedicated to amazing engineers, astronauts, scientists, explorers from around the world in delving into the wide world of space and our solar system. It's really exciting stuff. So thank you guys for joining us for that. We've got 7 classes joining us from across North America right now. So I want to give them a chance to say hi. We've got Miss Glaria's grade 6s in Brampton, Ontario. Hi, guys. Hey. We've got backpack swingers. Okay, that's a good start. We've got Miss Lackey's grade 4s in Freehold in New Jersey. Hey, guys. Welcome in. Awesome. We've got Miss Provencher's grade 6s in Longueuil, Quebec. Let me just get them demuted. There we go. Hey, we've got Miss Wilson's grade 8s in North Riverside in Illinois. Let me just find them. There's so many classes. There we go. Hey, guys. Awesome. We've got Miss Erickson, Miss Burns' grade 5, Stafford Springs in Connecticut. Hey, guys. We've got Miss Taylor's grade 8s in New Liskeard, Ontario. Let me just find them. There we go. Hey, guys. Awesome. And last but not least, we've got Miss Eggesdahl's grade 5s in Forest City in Iowa. Hi, guys. Awesome. Okay, you guys are super enthusiastic today. I love it. Of course, the reason you guys are all here today is for our speaker. So we are joined live in Pasadena, California by Ravi Prakash. So he is a systems engineer at the Jet Propulsion Laboratory at NASA, which is literally probably the coolest lab, coolest facility in the entire world. They put robots and things on other planets throughout our solar system. He's involved in the current mission that's on Mars. He's going to be involved in a lot more. I don't want to spoil his story, so I'm going to let him dive through what the work he gets to do is. So without further ado, thank you so much for joining us, Ravi, and take it away.
Thank you so much. So thanks everyone for joining. I am Ravi Prakash. So who here has heard of the Jet Propulsion Lab before today? Anyone? Raise of hands. Yeah, a few folks. So we are one of 10 NASA centers across the US. We are located outside Los Angeles, and we do robotic spaceflight. So we send robots to other planets. We send robots around Earth. We do things that typically don't involve astronauts, but we get to go further and farther because of it, because we can take more risks. And so I'm going to share a little video right now to talk a little bit about what we do at JPL, and then I'll talk a little bit about what I do and the work we do at JPL. So let's start.
What does JPL do?
It's the most unique place to work on Earth. Our charter is to do things no one's done before. We do what no one else even dares to dream about. Imagination and innovation are crucial in being able to do the kind of work that we do.
Innovation comes from people, but it also, I think, comes from structure and from the environment. If you can provide people with the appropriate tools, the appropriate workspace, the appropriate environment, you're also going to get a higher innovation output.
One of the things that makes the JPL environment so special to work in is that even when you first walk on lab, it feels like a campus.
When you walk around, you hear people talking about their work.
It would be the best way to get a subsurface vehicle beneath the Ice of Europa. And those people aren't just talking about it because they saw it on a movie somewhere. It's because they're really trying to figure out how to do it.
JPL is an incredibly diverse place. There's thousands of people here with big brains.
Planetary science, answering these big questions, you need chemists, physicists, astrophysicists, biologists, and then you need everyone on the engineering side to actually build the things that you need to answer the questions.
People know so much about so many different things that if I'm looking for an expert in a particular field, engineering or science related, I can probably find them at JPL. I don't have to pick up the phone, I just have to walk down the hallway. Science is all about asking questions, and engineering is all about finding solutions. And so it makes sense to marry these two things together and try and answer the biggest, toughest, most difficult questions we can come up with. What does JPL do? JPL builds the tool for exploring space.
Cool. So that's a little bit about what we do at JPL. I really enjoy being here. I'm really lucky to be here. I'm going to talk a little bit about my path to how I got here. So my entire life, I wanted to be a doctor, just like my dad. And it wasn't until senior year of high school that I decided, you know what, doctors work too hard and I'm too lazy. So I need to find a way to make lots of money and not work hard. So a lot of my parents' friends pointed me towards business. So I was like, okay, let me try business school. And immediately I realized that I was missing my math and science classes. And that was the stuff I enjoyed in high school. And so I said, okay, this isn't for me, what is? And I grew up near Houston, Texas, and Johnson Space Center is there. And that's where, you know, Houston, we have a problem. That's where like mission control is for the astronauts. A lot of space goes on in Houston. And so I remembered that anytime my family would go visit Johnson Space Center, I'd be really excited. And so I decided, okay, I want to be an astronaut now. So I switched my major from business to aerospace engineering. I went to the University of Texas and majored in aerospace engineering, got a bachelor's degree there, then went to Georgia Tech to get a master's degree, and then went on to JPL. And I've been here since 2005, minus a brief stint where I went to Northern California to do some work for nonprofits for 3 years, and then I came back to JPL. So I've been here for quite a while. I've worked on some really cool stuff. So this picture you see in the top left is a picture of me next to the test model of the Curiosity rover. So this is a car-sized rover that we landed on the surface of Mars. Let's see, it's been probably like 6 years now since it's been on Mars. It's trying to look for signs of, could Mars have supported life in the past? And so it does some really cool things. It's a beast. And I'll show you a video in a little bit about how we landed that rover on Mars. Shortly after that mission landed is when I took a break from JPL and I worked for nonprofits to try to figure out how can we engineer solutions to help people out of poverty. And so what was great about this is that, you know, at first I was like, you know, I can design spaceships, but I don't know if I can design something to help lift people out of poverty. It sounds so different. And what's great about engineering is that you can use that same process, the same design process, to solve any problem in the world. And so that same design process of brainstorming solutions and coming up with ideas and prototyping can be used for spacecraft, or it can be used to help, you know, solve world hunger. And so that's really great about engineering in my mind. Then I came back to JPL just a few years ago, and I worked on the InSight mission, which landed just under a year ago. And this mission is the picture of the spacecraft you see is in the bottom right. This is a spacecraft that doesn't have wheels, it's just a lander, but it's trying to understand how did Mars form as a planet, and also how did Earth and other rocky planets form. So it's listening for Mars quakes, which is, you know, it's like earthquakes, but on Mars we call them Mars quakes, and it's already discovered several Mars quakes in its short time there. And we're hoping it's going to find a lot more and teach us a lot more about Mars. And the picture in the top right is just my adorable family, who I'm really excited about. So we do a lot of stuff with Mars here at JPL, and I'm going to show you a video of how we landed the Curiosity rover on Mars. It took us, I think, almost 8 months to get to Mars. Mars is really far away. The trip itself is over 100 million miles. We come into Mars really fast, more than 5 times as fast as a speeding bullet. Because of that, when we slow down, we get really, really hot. And so the surface of this heat shield, the surface of the capsule, gets almost as hot as the surface of the sun. So we had a special material we designed to withstand that heat. We built the world's largest parachute. It's over 7 stories tall. We do this crazy maneuver called a sky crane maneuver. Basically, a rocket backpack lowers the rover onto the ground. And then we cut off and let go, and then we can start our mission. And so this was a really creative way that a bunch of people, engineers at JPL, had to think of to land a car-sized rover on Mars. The other rovers we had landed on Mars were a bit smaller, the size of maybe your school desk. And so we used airbags for those, but that would not cut it for this size rover. And so it was cool to be part of a team that got to invent a brand new way to land a rover on Mars. And now that rover's still chugging along. It was designed to last 1 Martian year, which is about 2 Earth years, and it's still going strong on Mars. So that was really fun. We do other stuff besides Mars, and so this is a spacecraft called Juno, which is going around Jupiter right now. It is teaching us amazing things and finding amazing pictures about Jupiter. So this is helping us understand how did Jupiter form as a planet. So we've had missions that teach us how Mars formed as a planet, how Earth forms as a planet, and now how these gas giants like Jupiter form. The image that you see on the bottom left, maybe some of you have heard of the Great Red Spot on Jupiter. So this is a massive storm. It's been going on for hundreds of years. That storm itself is bigger than Earth. It is the size of at least 2 Earths. We think it is shrinking over time. So maybe around like 2040 will be quite a bit smaller. But this is just a massive storm that keeps going around Jupiter. So imagine like a hurricane that is more than, it's more than twice as big as Earth. It's just really massive, and it's really, really exciting to see these things up close and to learn about it. And yeah, we love the pictures that come back from our missions. There's another mission that we're doing. So we don't just go to planets, we go to moons as well. And there's a moon around Jupiter called Europa. What's really exciting about Europa is that it's a ball of ice. And we think that under this ice is an ocean of water. And what we know about water on Earth is that when we find water on Earth, we tend to find life. And so we think that Europa is one of the best chances of finding life outside of Earth in our solar system. And so this mission, it's in the very early stages. It's pretty much a blank piece of paper, and engineers right now get to design, how do we want to explore this planet? This one is going to land on Europa, and you're going to see that we took some inspiration from how we landed that rover on Mars. We're doing something similar where we have rockets, we lower the spacecraft on some rope, and then we land it, and we cut off that rope and start the mission. This is a really tough mission because there's a lot of radiation on Europa because Jupiter has lots of radiation, so it gives that radiation to its moons. It's really, really cold because it's a ball of ice and it's really far from the sun. And so there's a lot of challenges that this mission has to withstand, which is why this mission is only going to last on the order of, let's say, a few weeks to a month, whereas other missions that go to Mars can last much longer. This mission is going to, we're still deciding what this mission exactly is going to do, but most likely it's going to try to understand the surface of Europa. And this animation, the example they show is maybe we drill a little bit, maybe we'll scoop a little bit, put some of that sample inside the spacecraft to be analyzed, and return that data to Earth that shows, this is what we think this is composed of. We don't bring these spacecraft back to Earth. We leave them on Mars, we leave them on Europa, because to bring them back to Earth means we have to launch another rocket that has a rocket just to send that stuff back. And so instead of launching a rocket to Mars, we'd usually rather launch more spacecraft to Mars. The exception is we are planning on bringing back a sample from Mars pretty soon in the next, maybe 1 or 2 decades. This is a cool mission. So actually JPL is, we're only peripherally involved in this mission. The main people that are designing this mission are at Applied Physics Lab, which is on the East Coast. And NASA has funded them to send a helicopter to Titan. Isn't that great? So Titan is a moon of Saturn. What's cool about Titan is that this moon has a lot of methane. Methane is carbon-based. And what we know about carbon on Earth is that when we find life on Earth, there's always some carbon composition. And so Titan is another good opportunity to find life outside of Earth in our solar system. And it's really cool that we're sending a helicopter. What's great about a helicopter is that it can explore farther and further than rovers can. Rovers, they actually move pretty slow. We want to make sure that they don't run over something that's going to be an obstruction. Helicopters can fly right over hazardous areas. They can go farther, and it's really cool to be able to design a helicopter that's going to go on another moon.
Hello there!
We do a lot of stuff on other planets, but we actually have more satellites around Earth than we have around other planets. JPL is one of the leaders in trying to understand the effects of climate change and how our Earth is changing over time. And so we have spacecraft that are understanding how the temperature is changing, how the oceans are rising. And all of this is so that we can make better decisions about how to take care of our Earth, because it is the only one we have. It's the only one that we know we have life on. And we want to protect ourselves for future generations, for you guys, for your kids and their kids. And so we have to really take good care of our Earth. JPL is one of the leaders in understanding how we can do that through this data of sending satellites around Earth. Other stuff that we do that benefits Earth is we're building robots that have artificial intelligence. And so these robots, can go into hazardous areas and help save people. So let's pretend there's an earthquake or a tsunami and buildings are collapsing. It's dangerous to send people to go in and rescue other people. We can help mitigate that risk by sending robots instead. So we're designing robots that can go maybe put, take away rubble. They can go into places with chemicals, dangerous chemicals, turn off gas pipes, do all these things that are dangerous for people to do in order to save more people. And so it's cool because at JPL, we're not only doing stuff to explore space, we're doing stuff to help everybody on Earth. And these types of robots have been used in natural disasters. They've been used to, I think, in tsunamis. And so it's really great that the stuff we do helps people on Earth as well as helps us understand and inspire people all around the world. This is, I think, my last slide. So this is just, how can you learn more about the work we do? How can you be more involved in space? Go to this website, eyes.nasa.gov. You'll download a little app for your computer, and you can really get in depth about all the spacecraft that we have. You can explore our solar system. You can really drag around the universe and understand our place in it. It's a really great website. I encourage all of you to go there with your parents' permission, of course, and learn all about it. So that's all I have for this. I would love to answer questions that you guys might have.
Outstanding. Well, thank you so much, Ravi. That was awesome. Before we dive into the questions with live classes, I want to note we've got about 4 groups watching on YouTube right now too. So if you guys want to just let me know what grade you guys are in, where you're coming from, I'll happily pass along questions. But yeah, let's start out. Miss Galeria's class, if you guys want to kick us off with a question, come on up. Let's see if we can get you muted. You should be good. Oh, let's see. No, okay. We can come back in a second, guys. You're still muted. I can't demute you for whatever reason. So, yep, now you're good. Okay, go for it.
Have you put the volume up too?
Yep, you're good. Any questions in Brampton?
No.
No? Okay. I'll come back in a second, guys. All right, Miss Lackey's class, if you guys have a question, come on up.
If you got to the planet, to the moon Europa, and there is an ocean under the ice, how would they get to the ocean?
Good question.
That is a great question. So how do we get under the ice of Europa to an ocean? So this first mission that we're sending there is going to help us understand the composition of that ice and also how thick it is. And so that a future mission might find a way to go under it. We think that ice could be hundreds of miles deep. That's really, really deep. There have been ideas such as maybe having some sort of really hot nuclear device that can just melt through that ice and get to the bottom and maybe send a submarine or something. We don't know how we want to do it just yet, but it's something that I think a future group of people, maybe even you guys, can help design how we can go under the ice of Europa and explore and really see, is there life under there? Maybe it's like bacteria, maybe it's whales, who knows? We don't know.
Very cool. By the way, what an engineer's question. Way to go. NASA's asking that same thing.
That's
all right, let's go to Quebec. If you guys have a question, Ms. Provencher's class, come on up.
How did you feel when you were accepted to work on the NASA?
Yeah.
How do I feel working at NASA? Is that the
Like
question?
when you got accepted, like when you applied for the job, when you got it, what happened?
Oh my gosh, it was a dream come true. So I had the great benefit of my graduate school advisor, my teacher in grad school. He knew somebody at NASA. So he said, you know what, I think this person would be a good fit. They flew me out here. I interviewed, they asked a lot of tough questions. And lo and behold, I got the job offer, and it was really exciting because I am so excited about exploring space and building spaceships. I get to come to work every day and just do things that have never been done before. And it's really, really awesome. I am lucky every day. And actually, it's days that I get to talk to people like you that reminds me how lucky I am that I get to work at a place like NASA.
You are the most enthusiastic guy I've done like all month. So thank you for that. It's fantastic. All right, Ms. Wilson's class, if you guys want to come up, go for it.
Oh, and after this question, I'm going to show you the mission control room.
Oh, sorry, what was that, Ravi? Before we go to the question, what were you saying? Sorry.
Oh, I'm sorry. After this question, remind me, I'll show you the mission control room that I'm in right now. I'll give you a little sneak preview.
What? Oh.
Yeah, but please go for that question first. Sorry.
Yeah, best hang whatever. Okay, so Miss Wilson's class, yeah, come on up, guys.
You want to ask a question?
Hey.
CJ, you want to? Anybody want to?
What's up, dude?
Wait.
Do you want to? Oh no. Area 51. Tell me about it. What is the area? Be respectful.
Hey guys, if anyone has a question, let them ask it, okay?
Okay. Who has a question? Nobody has a question? All right. Nobody has a.
All right, we'll go to another class then, guys. So let's go to Connecticut, Miss Erickson, Miss Barnes' class, and then we'll take that quick tour, okay?
Great.
All right.
How did Saturn form its ring?
Ooh.
Can you repeat that, please?
Do you know how Saturn formed its rings, Ravi?
Oh, how did Saturn form its rings? So those rings are actually rocks. It's amazing, right? Because we think of it as looking like a continuous thing, but it's actually a bunch of rocks. Saturn's really big. So, the sun is big. The sun, when rocks go near the sun, they get captured in orbit around the sun. Same thing happens to Saturn. Saturn and Jupiter are so big that when rocks get close to them, they actually get captured into orbit around them. And so Saturn has, 60, maybe 70 something on moons. And those are like the big ones. There's also all these smaller, maybe school bus sized rocks, small is relative, and there's just, so many millions of those that go around Saturn. And those are what the rings are actually composed of. A lot of people don't know that Jupiter also has rings. So Jupiter, when we look at pictures of Jupiter, we tend not to see the rings. It's very small, very thin, but Jupiter also has rings around it. And there's other planets also that have rings as well that are further out.
Super cool. All right. Before we go to the next question, did you want to show us around?
Yes, I would love to show you this room. So this is the room that's sort of like our mission control. Whenever we have big events like landing on Mars or going around Jupiter for the first time, we have people in this room. People like the president have been in this room. It's really great. And so right now it's empty. We don't have anything big going on right now. Through that window, I don't know if you can see those windows, through there is where that room, all the data from all the spacecraft that are outside, beyond Earth, go into that room. So we call it the center of the universe. So data from Pluto, data from Jupiter, data from Mars, all that data is coming into that room. Even data from the Voyager missions. Voyager are missions that launched in the 70s, and they are at the edge of our solar system, if not beyond our solar system. They're the only spacecraft that have gone that far. They're so far that it takes more than a day to send a signal to that spacecraft and more than a day to hear a signal back from that spacecraft. These signals travel at the speed of light. So for example, if you're talking to the moon, it takes on the order of seconds at the speed of light to talk to the moon. It takes over a day, over 24 hours to send a signal to Voyager. It's so far away, and there's 2 of them.
Outstanding. By the way, I'm totally nerding out that you're in mission control. That's super cool. I'm going to pass along to classes at the end of this session just a video of the InSight lander when it landed and all the scientists and engineers being very, very excited, shall we say.
Yes.
Awesome. All right, let's go to Miss Taylor's class. If you guys have one, go for it.
Okay. Am I on?
Yeah, you're good.
Oh, okay. So what courses did you have to take through university?
What courses did you take, Ravi? Like how did you get to where you are?
What classes did I take in college? So, first I'll start with in high school, we had some electives, and I think I tried to focus on those that were maybe math or science oriented, but I also love other things too. And I think it's great that, everyone that, a lot of people that are here are very well-rounded. They're people that, whether it's some sport they're into or some hobby or arts and crafts, whatever it is, people have other passions besides space, and that's totally great. In college, I took a lot of math and science again, a lot of engineering classes. So these are classes like dynamics or orbital mechanics. Orbital mechanics is learning how things, if you're sending a spacecraft somewhere, what path do you send it to take? How do things orbit? If you want to go really far into space, maybe sometimes you do flybys of planets, which is like you go close to the planet, just close enough to get a good gravity assist and keep going farther. I took classes like structures to understand, if you have to withstand loads of a rocket, or if you want to build something that has to carry a lot of weight, how do you design that? A lot of thermal classes, like thermodynamics. So understanding there's, when we enter Mars and it gets really hot, what can we do about that? And so it's really a whole range of classes. I did engineering. There's a lot of scientists at JPL also. So people that focused on biology or chemistry, different things, so that when we go to these planets, we need scientists to tell us, what instruments do we need to carry? Hey, help us interpret that data. to tell us what this planet is composed of, or is there life on these planets? And so it really takes all different types of people. I'm an aerospace engineer. There's all types of engineers here. There's mechanical engineers, chemical engineers that help design the rockets. You know, there's thermal engineers, structural engineers, all types of people. There's business administrators to help us. You know, these missions cost billions of dollars. And so we need to manage that money. And so there's business people that help us do that to make sure that we are staying on track and on schedule.
I'm really glad we got to that point too. Whenever we're doing things in research vessels in the ocean as well, like if you want to be involved in really cool science and engineering, there are a ton of different jobs and ways to do that. So that's awesome. All right, let's head to Forest City, Iowa. If you guys have a question, Ms. Eggsdahl class, come on up.
Go ahead. No. She's got a question. Sorry.
What is the most exciting part of your job?
Oh, the most exciting part of my job. That's a good.
Oh, sorry. There you go. Sorry, go ahead.
So I mean, honestly, I do love talking to everybody else about the amazing work we do. That's one of my favorite parts. I think on a day-to-day basis, I love working with the people on my team. So everything that we do is in groups. You know, you go off and maybe do a little bit of work by yourself, but there's a lot of meetings where you're just collaborating and discussing ideas and tossing around, hey, how should we do this? How should we solve this problem that's never been done before? And so that's my favorite part, which is working with a group of people and just trying to solve a problem together. It's something that, you know, funny enough, in school, you tend to work a lot by yourself, but when you start getting to college or you start getting to the workforce, that's where you really work in groups. And so I encourage students as much as they can to work together, to try to solve problems together. And it's great to have like group activities as much as possible.
Very cool. All right. I promise there's some groups on YouTube. So we've got a group, Miss DeCaro's class in Maple, Ontario, wanted to ask, what's the longest time it took you to build a robot? And you can segue this into like how long it takes to typically build a lander or whatever you'd like. Yeah, that's such a good question. So, you know, when we have an idea for a mission, it's usually there's two ways we do it. One is NASA sometimes says, hey, we want you to do this very specific mission. Like on the Curiosity rover, they said, we want you to send this big rover to Mars and, you know, try to find out, could Mars have had life in the past? So that's a very specific mission that we say, okay, we're going to, you know, design how we're going to do that on a blank piece of paper. We're going to build it, we're going to test it, and we're going to launch it. All that actually takes like 10 years for something that big. We have other types of missions, which are, NASA says, we have a pot of money. We want you to tell us what you would do with that pot of money. It's really cool. And so I'm starting to work on this mission to an asteroid where we're going to explore the only metal asteroid we know of in the entire solar system. We're going to orbit it, and we think it used to be a planet and understand, was it a planet? If it was, we can probably understand how Earth formed as a result of exploring this asteroid. So this, you know, there's a group of people that said, okay, I have an idea. I think I want to explore an asteroid. So they write up a paper about it. It's with a big group of people. And NASA says, okay, let me look at everyone who submitted an application for this pot of money. And I'm going to select, you know, a few of you to do a little more analysis on your idea to see, is it a good idea? So we got selected for that. Then out of those, they say, okay, now we're going to select one to get a lot of money to do this mission. And so this mission got selected. It's an asteroid mission. From the time that we started writing that initial paper to this time that we're going to launch, which is in a few years, it's probably, again, like 7 to 10 years. So these things take a long time. So some people, they work on these missions from beginning to end. Some people join in the middle. I joined somewhere in the middle because like this mission was already accepted, which means now we have to build this thing. We have to design this thing. We need a lot more people to do it now. And so that's when they bring on more people. Soon we're going to start, you know, building and testing the spacecraft, which means we need even more people. And so some people join at that phase. And then when we launch, we have to operate the spacecraft. And that's when other people join and more scientists join. And so these missions do take a long time. Some people work on it from, you know, beginning to end, and some people work on it for a short time. Outstanding. Thank you so much. All right, Miss Galeria's class does have questions now, so we're going to go back to them. You guys have one? Come on up.
What's Ravi's favorite planet?
My favorite planet. Ooh, I do enjoy Earth a lot, I have to admit. My favorite planet is probably actually a moon and not a planet. I love Europa. I think that it'd be really cool to try to go under the ice into the ocean like that one lady asked, and to explore, is there life under there? I have such a good feeling that there's, you know, it is our best chance of finding life outside of Earth in our solar system. And I have a really good feeling about it. So I really want to work on a mission that does that.
Yeah, I'm really happy we got to Europa too. Almost every time we talk to someone from NASA or other space agencies, Europa is like,
We're all so excited about it.
awesome. All right, Ms. Wilson's class also has a question. So if you guys want to come up, if your video's off. I don't know. Let's see. Well, their question was, how many different moons are there, Ravi?
There are probably within our solar system, there are hundreds of moons. But what's great is that they're very unique. So our moon, we think, may have come from Earth. It may have been like some big asteroid that hit Earth, a piece broke off and it formed. You have other ones that are like around Jupiter, you have a volcanic one. So you have one that is spewing like sulfur compounds. I think it's called Io. And what's funny is around Jupiter, you also have the icy one, which is Europa. And so around the same planet, you have very different moons. One ice, one is like blowing steam out. And so there's just so many different kinds of moons that it's great. And I hope one day we can explore all of them.
Cool. All right, Miss Lackey's class, if you guys have one, another one, come on up.
Ferris, I'm gonna ask you a question. Good, thank you. You know what? We're gonna pass. Sorry, we didn't know you were coming back yet.
All good, no worries. I'll come back to you guys in a minute. All right, let's go to Mr. Vanche's class. Come on up, guys.
Do you have a plan to do like are you planning to do something in the future, like another big thing, like robot, like something like that?
Yeah, any big missions that you guys are planning?
Yes, that is a good question. So there's always something big up in our pipeline. So right now we are building another rover that's going to go to Mars. This rover is going to grab some dirt and put it in a can on top of its belly. Then we have another mission that's going to go to Mars, grab that can of dirt, and bring it back to Earth. And so that's a mission that we call Mars Sample Return, because we're returning a sample to Earth. It's the first time that we'll have brought something back from another planet. And what's great is that is the best way to figure out, does that piece of dirt, what can we learn about that piece of dirt? Are there actually little pieces of life, like bacteria in that dirt? Any molecules? What is Mars made out of? These robots that we send, they're very smart, very sophisticated, and they can do a lot of great science, but there's nothing that can replace the human brain. And so when we have the world's best scientists look at that piece of dirt, they will tell us so much more about Mars than we ever knew. And so, it's funny. So this rover, Curiosity, has been on Mars for 6 years, and it's gone just a few miles. You could send a human being to Mars, and within 30 minutes, they'll have learned more than that rover. And so it's just that what humans can do is just so great and can't be replaced by a robot. And so we are excited about doing that. There's also, that Europa mission is one of our bigger ones too. Right now we're designing a mission to orbit orbit Jupiter and learn a lot about Europa. And after that mission is when we will land on Europa, like that video that I showed earlier. And so those are also just really big missions that we have downstream.
Very cool. And speaking of Jupiter, you mentioned that the Great Red Spot is moving around Jupiter. So my understanding was that it was stationary, so it's actually going around the planet, or
it is circling the planet. Exactly, it is orbiting Jupiter. So just like hurricanes move around Earth, they move on Earth, but they die down. This one has just been going for hundreds of years, and hundreds of years is just all we know, because there were observations of this red spot 300 years ago. It might have been going on for way before that, like let's say thousands of years. We don't know. And so it's great to learn about how this thing has been forming, how it's been changing over time. Right now it looks like it's shrinking, but is it going to actually grow later on? We don't know. And it's cool to learn about these things.
Outstanding. All right, Miss Lackey's class, do you guys have a question now, second one?
Yes.
Yeah.
Nice and loud, okay?
How far can Voyager 1 and 2 go before we lose connection?
Ooh, how far can Voyager 1 go before we lose connection? So that spacecraft is really far away. A lot of times, what we had to do is, because it is nuclear powered, but it has been losing power over time because these nuclear sources lose heat over time, and that just makes it have less energy. So we've actually had to turn off a lot of the science instruments. So the only things that are remaining on this are the ability to talk to Earth and like a few sensors that maybe tell us like the pressure outside of the solar system. The thing that will make it stop talking to Earth is either it loses the power, so it doesn't have enough energy to talk, or it's too far away. I don't know how far away is too far away. I'm guessing that it will lose power before it's too far away, because these beams are really strong and powerful and can point towards Earth from really far away. So it's a good question. I don't know the exact answer, but I think it's going to be a while before it's too far away. I'm guessing it's going to lose power first.
Yeah. And you mentioned Voyager twice now, and I just want the classes to know, can you tell us a little bit about the golden record on Voyagers, because they're so cool?
So this is really cool. So there was a scientist named Carl Sagan who had this idea that we're sending these things so far away that what if, this thing, there's something that we put on the spacecraft that can last over 100 million years, so that if it's just careening through space, some other civilization might find it, some alien species might find something and learn about us. So they decided, let's put this golden disc on the spacecraft. On this disc is sounds of Earth, it's images of people and animals on Earth, it's music, it's recordings of all these different things. And it's good. It's the idea is that it would give any alien species a glimpse of what life was like on Earth. We will be long gone by then. This will be something that future species will find like millions of years from now. Maybe even when the Earth is no longer, the sun is no longer, the solar system might be no longer. But they will be. It's like a little timestamp about what life was like on Earth.
Yeah, a message in the bottle in the cosmic ocean.
Yeah.
Cool.
That's
All right. Ms. Wilson had another question, and we always get this question when it comes to space missions. How much do missions cost?
Yes, these missions range in price quite a bit. So the ones that NASA tells us to do tend to be the more expensive ones. They can cost upwards of $1 billion. The Mars rover that we sent to Mars, that mission from design all the way through operating this thing is about $2.5 billion. That sounds like a lot. It is a lot of money. When you think about it, if every person in America bought a movie ticket, that would be more than this mission. And we think that these missions are movies worth seeing. We think that the inspiration they provide to people all around the world in America, the way they inspire children to go into math and science, and the innovations that come out of these technologies are well worth this money. The mission that I'm working on now it's one of the competed missions, the ones that we had to write a proposal for, say we're going to do this mission. Those tend to be a little cheaper, on the order of, let's say, $500–700 million. Still a lot of money, but these missions, they answer the questions that we have been wondering for eons, which is, how did life get on Earth? How did our planet form? Why are we here? And so we get to answer these big questions, thanks to the American people funding projects like this.
It's a great analogy to say that, if all the money that the U.S. particularly invested in stuff was $1, it's about 4/10 of 1 penny goes towards NASA. So it's this really good tiny proportion that leads to so much innovation and exploration, which is fantastic. All right, let's go back to Connecticut. If you guys have a question, Ms. Erson's group, come on up. Yeah, you're good to go.
Go ahead.
How long does it take? How long does it take to get through Europa for seeing the ocean?
Great question. How long does it take to get to Europa? So this partly depends on what size rocket we send the spacecraft on. Europa is really far away. So I'm going to first talk about other planets. Going to the moon takes just a few days, going to our moon. Going to Mars takes somewhere between 6 to 9 months, depending on the position of the planets and how far away Earth and Mars are. Going to Europa is, basically we're going to Jupiter at that point. This takes like 7 years. It takes a really long time. So imagine you're working on this mission, you're designing the spacecraft, you spent 5 years maybe designing and testing the spacecraft. It launches, you're gonna work on a different mission for 7 years and then come back to this mission to see how it did. If you guys are in like 4th or 5th grade or something, you will be almost graduating high school if this thing launched today by the time it got to Europa. And so it takes a really long time because these planets are really far away. Hundreds of millions of miles away.
Yeah, well, I love you said at the beginning that Mars is 100 million miles away, which is just an unfathomable distance, and that's our closest neighbor. So
that's right, yeah.
All right, we're gonna take 3 more questions. One from a group online to Ms. Takiro's class wanted to ask, do you believe in Planet 9? And just in general, can you explain, you know, what the ideas are behind maybe things that are in our solar system that aren't, you know, visible to us?
Yeah, so there are, you know, we often see planets that are orbiting, you know, things that are orbiting the sun that are pretty large. And so, you know, when I was a kid, Pluto was considered a planet. Pluto, it has a very elliptical orbit around the sun. It's elliptical means oval shape. So a lot of the planets pretty much orbit in a mostly circle around the sun. And Pluto had this really oval orbit, and it's small. It's, I think, I want to say smaller than our moon. Don't quote me on that, but I think it's maybe smaller than our moon. It's really small. And so a lot of people were saying, you know, it's more like a really big asteroid, maybe more like a moon than it is a planet. And so they were saying, let's demote Pluto from being a planet. But since then, we've also found other things that have these, you know, really oval orbits around the sun that are fairly large. And so people say, you know, should we call it a planet? Should we call it an asteroid? What do we call it? And it almost doesn't matter what we call it. The point is that it's orbiting, you know, it's not going to change what it is, which is just a big rock orbiting the sun. And so there's been, you know, thoughts about these other, you know, are there other planets around our solar system? Hard to answer. There's a group of people that actually make these decisions, and to me, it doesn't matter. But it's kind of a fun conversation to have.
Certainly is. All right, last two. We'll go to Miss Taylor's class first. Come on, guys.
How many robots did you guys build?
So JPL, Jet Propulsion Lab, was actually formed before NASA was a thing. It was a group of grad students at Caltech, California Institute of Technology in California, who wanted to build rockets. And they ended up launching America's first satellite into space. So that was the first one. Since then, we have launched probably over 100 satellites, whether it's around Earth or other planets. I don't know exactly how many. I know that it's been a lot, and there have been successes and failures. We learned a lot from the spacecraft that failed because we have to do a real deep analysis on what went wrong, what do we fix so that it doesn't happen next time. And so we don't look down on failure so much. We look at it as a learning opportunity. But yeah, we've launched, I wish I had a number. We've launched well over 100 spacecraft all around our solar system.
Wow, very cool. So two things I wanted to mention, speaking of failure, our session literally yesterday with Babak Ferdowsi, if you guys wanted to see about spacecraft failing and how that's happened over time, he did a great presentation on that. So do check that out on our YouTube page. And secondly, I totally lied. We have a second class that wants to ask a second question. So Miss Galeria's class, come up first, and we'll go to Miss Eggesdahl to wrap up, okay? So Branson, come on up, guys.
Ask a question. Hold on.
Take your time, all good.
Yeah, ask a question.
Hey.
I look in here.
Yeah, you're good.
How long does it take to build a rocket ship or a space shuttle, and how many engines do they have?
Good question.
Yeah, how long does it take to build a rocket or space shuttle, and how many engines does it have? So these are, you know, building rockets is, it's similar to building spacecraft in that if you're building something that's new, you have to start from a blank piece of paper and then go and then, you know, design it, build it, test it, do all that stuff. And it takes several years. Rockets nowadays have been a little more, it's because we've done it so many times in the past, the companies that build rockets can build it much faster than, you know, 10 years. And so they can build rockets, probably several rockets within a year. It's because the design part has already been done. And so now it's really just building, testing a few of them, and then you can just give it to someone who wants to launch a spacecraft. I will say that, you know, generally NASA doesn't build rockets. NASA's job is to do things that have not been done before, and rockets have been done now. And so with the exception of a really big rocket that NASA's building to send people back to space, we have companies like Lockheed Martin and Boeing and SpaceX that are building rockets that NASA can just buy and say, okay, we're gonna buy this rocket, but we're gonna build the spaceship and design the spaceship that goes on it. It takes a lot of people to do any mission. So for our space missions, we have usually in a mission, no matter how big it is, over 1,000 people at some point have done something with that mission. And every single person matters. So I love this story that our chief engineer at JPL, his name is Rob Manning. He told a story about there's these Mars exploration rovers that went to, two rovers that went to Mars, and they landed using airbags. So these airbags inflated around the rover and helped it land softly. There are these old ladies somewhere in America who sew the airbags together. If one of these ladies missed a stitch, the airbag might have not worked and the whole mission would have ended. And these, this company that builds these airbags, they build cloth for other reasons. They don't do it for space missions, but they happen to do it for our mission because we knew that they could do it for us. And so, so many people just around so many disciplines had something to do with every single mission of ours, and every one of them has to do their job right. Otherwise, the mission could fail.
Outstanding. It would be a great answer to end on, but we've got to go to Ms. Egglesdall's class, so we want to bring you guys back up. So come on down, guys. Yep, you're good to go.
What are meteors made out of?
What are meteors made of? Is that the question?
Yes. Yes.
Yeah. Okay.
And it cut out when you repeated it. Can you repeat
so what are meteors made of, Ravi?
What are meteors made of? Oh gosh, you had to end on a hard question. So there are meteors typically made of just rocks. There's meteors and comets I will say tend to be balls of ice. And fun fact about meteor is that when you see that tail of a meteor, it's usually because the sun is shining on that comet, that ice is melting and it's causing that trail of ice. Meteors tend to be rocks. What's neat is that a lot of people who are searching for meteorites on Earth, they go to Antarctica. And that's because Antarctica is this white ice sheet. So when you see a dark rock there, there's a good chance that it's a meteor. And so, or meteorite or meteoroid. There's a difference between those words, and even I get confused.
Everybody's confused, don't worry. Well, thank you so much. That was marvelous, Ravi. So before we wrap up, I just want to say, is there any last message you want to share with classes where they can find out more? I'm going to pass along the Eyes Napa NASA site, the Insight Lander video. Is there anywhere else you want to point people to learn about the work you do or NASA in general?
Yeah, I love going to nasa.gov. I think that's a great place. There's a lot of other places for great space news. Also, I'll just say, whatever it is you're passionate about, just do it. I was doing business before, then I changed to space. You might know what you want to do, you might not. It doesn't matter. Just whatever you decide to do, just work hard, be passionate, and you will enjoy yourself.
Outstanding. Well, thank you so much for joining us today. What we do at the end of every Hangout, Ravi, I'm going to demute everyone's microphone. So boys and girls, if you guys could get ready to join me in saying a huge thank you, I'm about to demute absolutely everyone. So Ms. Lackey's class, Ms. Taylor's class, Erickson, Bravanche's, Valeria, everyone, thank you guys so much. Awesome. I love the enthusiasm, guys. Thank you so much for joining us during our Space Month. And Ravi, that was fantastic. Welcome back anytime, man. That was great.
Awesome. I love it. Thanks so much, everybody, for taking the time.